We have now completely solved the network. Here's our original network. I've designated the currents as such. Through this 2R resistor, it's I1. This one's I3. This one's I2. This one's I4. The positive directions are going left to right. And we have the small I as the current in our bridge resistor and cap I as the current supplied into the network by the voltage source. The values that we determined is that the current supplied by the voltage source is just 5V over 7R. The current in the bridge resistor is downward, that's positive direction, with value V over 7R, and currents I1 and I4 are equal at 2V over 7R, and I3 and I2 are the same at 3V over 7R. So those are all the currents in the resistors in the network. Now, I'm going to show you another way, a very powerful technique for solving a network. It's a technique that I use for most of the complicated networks that I have to deal with. I'm just kind of partial to what's called node voltages. Node voltages makes use of Kirchhoffs current law. Now I'll redraw the network here. This is 2R, this is R, 2R, R, and R. And this is node Y, and this is node X. The voltage source has value V. Now, in the method of node voltages, you first have to establish a reference node, which will be at zero potential. And I'll let this node here be our reference node, or the ground node, which has 0 volts as its potential. Now, all voltages in the node voltage technique are referenced to the reference node. This is our reference. Now, some of the nodes we know the voltages for. We know the voltage at this node. This is our reference node. We also know the voltage on this node. It just happens to be the battery voltage. So the voltage on this node is V. Everywhere along here is voltage V. Now, we don't know the voltage at Y or the voltage at X, so we give it an arbitrary designation. I will call the voltage at Y Vy, and the voltage at node X as Vx. These are unknown. So we have two unknowns in the network, so we have to come up with two equations to uniquely solve this network. So what we do is we now establish a positive direction for our current flow. I will use currents leaving a node as positive. We could also choose currents entering a node as positive. It doesn't matter. It all comes out in the wash. But once you establish a positive direction for your current flow, you have to stick with it. If you don't stick with it, if you change somewhere midstream, you're going to get all buggered up. So once you establish a current convention for positive current, you have to stick with it throughout the whole network. So I will have currents leaving as positive. So looking at node Y, these will be my currents. And at node X, my currents will be like this. Currents leaving is positive. So now what we do is we use Kirchhoffs current law at node Y. So Kirchhoffs current law on Y is telling us that the summation of the I's, K's at Y have to sum to 0. That's Kirchhoffs current law. All the currents summing either entering or leaving the node have to be 0. So writing it for node Y, the current through this resistor is going right to left, and that's the polarity on the resistor, the voltage polarity. So to establish the current in the positive direction, we take the voltage on the positive entering is positive, and we subtract off where it's leaving. So on this end of the resistor, it's Vy minus the voltage on this end, which is V. And then we divide by R to get the current. Then the current through this resistor will be Vy minus Vx. And we divide by the resistance, R. And the current through this resistor will be Vy minus the voltage on this end. Well, this is our reference node. So this will just be Vy minus 0, or just Vy divided by 2R. And that's going to be equal to 0. Now I'll clear out the denominator by multiplying through by 2R. So we have 2 times Vy minus V plus 2 times Vy minus Vx plus Vy is equal to 0. Now we gather up like terms. We have a 2Vy, a 2Vy, and a Vy. So that's 5Vy. Then a minus 2V and a minus 2Vx is equal to 0. I'll move the 2V. This is a known. This voltage is known. I'm going to move it to the right-hand side. So we have our first equation. Equation 1 is V, or 5Vy minus 2Vx equals 2V. That's our first equation. Now, at node X, we do the same thing. We'll take the current leaving as positive, so the current through this resistor is Vx minus the voltage on this node, which is V. So we have Vx minus V divided by the resistance, which is 2R, plus the current in this resistor, which is Vx minus Vy. We're going in this direction, so it's Vx minus Vy over the resistance, which is R, plus the current in this resistor, which is Vx minus 0, or just Vx over R, and that's equal to 0. Again, clear out the denominator by multiplying through by 2R. So we have Vx minus V plus 2 times Vx minus Vy plus 2 times Vx, and that's equal to 0. Gathering like terms, we have a Vx, 2Vx, and 2Vx, so that's 5Vx minus 2Vy plus, or a minus V, forgot that. So 5Vx, a minus V, and a minus 2Vy. I'm going to move the known V over to the right side. So we have 5Vx minus 2Vy equals V. So this is equation 2. We have 2 equations involving 2 unknowns. We can solve the equation, we can solve the network exactly. Now, rather than adding, subtracting equations like I did before, I'm going to use a little different method. We're going to use some matrix methods on this one. So what we'll do is we'll write our 2 equations up here first. So we have 5Vy minus 2Vx equals 2V. Well, I'm going to write it a little differently here. I'm going to put the x's, the Vx first. So I have minus 2Vx plus 5Vy equals 2V. That's equation 1. Our equation 2 is 5Vx minus 2Vy is equal to V. So those are our 2 equations involving our node voltages Vx and Vy. So I'm going to put it in matrix form now. I can write this as an augmented matrix where I've got minus 2, 5, and then 2v, and 5, minus 2, v. This is my Vx column, this is my Vy column. Now, something important to note here. This is always true of networks. If you have a passive network with no dependent sources, you just have independent sources, no dependent sources, your matrix involving the network elements is always going to be symmetric. You can see with minus 2, 5, 5. The elements on the diagonals up on the elements opposite the diagonal are always going to be equal. So if I had, say, a more complicated network, the matrix will end up being symmetrical as long as you don't have any dependent sources. If you have dependent sources, then the matrix gets skewed. But for a network where you just have independent sources, you always end up with a symmetric matrix. Now, what I'm going to do is I'm going to call this row 1 and this row 2. So first off, what I'm going to do here is I'm going to take 5 times row 1 and add it to twice row 2. So our matrix, we're not changing row 1, so we'll have minus 2, 5, 2v. Now, I take 5 times row 1 and add it to twice row 2. So minus 2 times 5 is minus 10, plus 2 times 5, positive 10, that's 0. 5 times 5 is 25, plus twice minus 2, so we have 25 minus 4, or 21. And then we have 5 times 2v, which is 10v, plus 2 times v, or 2v. 10v plus 2v gives us 12v. Now what I'm going to do here is on row 2, I'm going to simplify it by dividing through by 2, or by 3. So dividing through row 2 by 3, I get 0, 7, and 4v. Now what I'm going to do is I want to make this 0 in here, so I'm going to multiply row 2 by minus 5, and I'm going to add it to 7 times row 1. So writing this, I'm not going to change row 2, so we have 0, 7, and 4v. Now I'm taking minus 5 of this and adding it to this row. So if we look at it, 7 times row 1 is minus 14, 35, and 14v. And I'm going to add to it minus 5 times 0, which is 0. Minus 5 times 7 is minus 35. And minus 5 times 4v is minus 20v. So when I add them, I get minus 14, 0, and minus 6v. So that's what comes up in here, 0. Minus 14, 0, minus 6v. Now, this is my Vx column, this is my Vy column. So I can write the answers. Minus 14 Vx equals minus 6v. And on this row, we have 7Vy equals 4v. So solving for Vx, Vx is minus 6v over minus 14, which gives us 3v over 7. And Vy is 4v divided by 7. So those are our node voltages. So Vy is 4V over 7, and voltage, node voltage Vx is 3V over 7. Now we can get the current I in the network, the little I, through this resistor. If we look, just get rid of this here. What we have, our small I current, let's say we define it that way, then our Y node, Vy, is 4V over 7, and Vx is 3V over 7. So I, and the resistor is R, so I then will be Vy minus Vx over R. And this is, Vy is 4V over 7 minus 3V over 7. So this becomes just V over 7 in the direction from node Y to node X. And that is the same value that we got before. Oh, this is over R. Forgot my R. So, V over 7R. This is small I. Now, we could use this. We can solve for these other currents if we wish to. Let's just look at what we have here. We have that Vx is equal to 3V over 7, and Vy is 4V over 7. Now let's just solve for a few other currents, just to show how it works. Now, if we want, say, the current in this resistor, which we call I3, let's just, let me rewrite this. Suppose I use a different designation for the currents. I'll show you how that works out. This is 2R, R, R, 2R, and R. Let's choose this current. Let's just call this IA. Now this is Vy and Vx, and we have voltage V at this node, and this node is 0V. So if I want to compute IA, IA will be this voltage minus that voltage divided by R. So this is Vy minus V divided by R. Voltage at this node is Vy, voltage at this node is V. So Vy minus V divided by R. Well, Vy is 4V over 7 minus V over R. Well, 4V over 7 minus, this is 7V over 7. So this becomes a minus 3V over R. So this tells me that IA is actually in the other direction because we have a minus sign. So IA, or the current flowing in R, is actually going from left to right, and that's what we see here. Our I3 is a positive 3V over 7R. Or we could write that IA equals minus 3V over R, which is minus I3. That is, IA is pointing opposite to R3, or I3. Now, one other, let's just choose this is IB. So IB then will be this voltage minus this voltage divided by 2R. So this is V minus Vx over 2R. Well, V minus Vx is 3V over 7 over 2R. Well, V minus 3/7 V is 4/7, or 4V over 7, divided by 2R, which is 2V over 7R. That's IB. It's positive, tells us that the current is actually flowing in this direction from left to right. Well, let's compare it to I1. Well, I1 is positive 2V over 7R. So again, we get the correct value. Now, I'm going to show you one last technique in which to solve this network, and I'm going to be using what's called a delta to Y conversion. I'm going to use a network transformation to do it. And it gets a little involved, but you'll find that it's a clever way to look at solving the network. Before I use the delta to Y conversion, I'm going to redraw the network so you can see the topology and how it works. Here is our original network. We had a V, we have two arms of our bridge with our resistor R in between nodes X and Y. I'm going to redraw this network in this fashion so you can see the delta. We have a delta in here. Now, this node here, going to the positive end of the voltage source, is just this node. Everything along here has just been brought together to a single point. And the same thing down here. This node on the minus end of the voltage source is all this node right here, and they're just brought together. R and 2R brought down together. It's just like I've connected there and connected there in that fashion. And you just redrew it. You can see that we can write it like that way and do the same thing here. Connect is that fashion. That's what I have here. Now, there's a transformation called the delta to Y, or some people call this star connection, or this is delta to Y. Now, the delta to Y conversion works like this. If I have a delta connection, the delta comes from the Greek letter delta, because it looks like a delta. Now, if I have three resistors or three elements, network elements, connected as so, and I will call this, say, ZA, this is ZB, this is ZC. These can be generalized impedances. They could be resistors, inductive, capacitive, reactant, doesn't matter. But for our network here, these are just resistors. So this could be RA, RB, RC, but I'll just use the generalized impedance Z. So this is our delta connection. Now this is entirely equivalent to a Y connection, or what some people refer to as a star connection. If this is node small a, this is A, this is node small c, this is node small b. Now, I will call this element Z1, this one Z2, and this one Z3. Now, we need to determine the values of Z1, Z2, Z3 in terms of these elements, ZA, ZB, ZC. And this is our Y connection. This is delta, and this is Y. Now, going from delta to Y is pretty easy. It's an easy equation to remember, to convert from the element values A, B, Z, B, C to Z1, Z2, Z3. define ZT as ZA plus ZB plus ZC. Remember, we're going in this direction, delta to Y. So we have a total resistance, ZA, ZB plus C. We add all the three elements together. Then Z1, the Z1 is in here. And it is adjacent to ZA, ZB. So Z1 is ZA times ZB over ZT. Z2 is this one right here. That's our Z2, and it's adjacent to ZA and ZC. So Z2 is ZA, ZC over ZT. And Z3 is this element here, connected to node A. This is my Z3, and it's adjacent to ZB and ZC. So this is ZB, ZC over ZT. So that's the conversion. Now, let's look at our network here. We can see that we have a delta right here. That's our delta. So let's take our delta and write it here. This is 2R, this is R, and this is R. And we want to write this as a Y connection. But why do we want to do that? Well, the reason is you can see that if we can take this and make it a Y or a star connection, then we can solve for the total resistance or load that this voltage source sees. Sure. Let's take this delta here and convert it to a Y. And this is what we end up with. So between these three nodes, rather than having the delta, we're going to put in a Y. Now you can see that we have a series connection here, a series connection here. We can combine these two resistors, and then we have a parallel combination. We can get the equivalent, and then this parallel combination, series parallel combination, is in series with this resistor, and we can easily combine it and get what the total, say RT, is that the voltage source sees. Then the current, cap I, will just be V divided by RT. We can get the total current once we know what the load the network presents to the voltage source. So that's the motivation here for doing this. So here's our delta that we had. Now, to get this resistor, we first find our I'll call this R load, not to confuse. This is R load. This is not the same as this RT. So our RT will be the sum of the three resistors. So we got 2R plus R, which is 4R. That's our RT. Now, this element is just the product of the adjacents, R and 2R divided by RT. So this becomes 2R squared over RT, which is 4R. So this is R over 2. This element is the product of this and this divided by RT. So this is 2R times R over RT, which is 4R. Again, this is 2r squared over 4r, or r over 2 for this one. Now, for this element here, that's the one in between these two, so this becomes r times r, or r squared, divided by rt, which is 4r, so r over 4. So those are our element values. For this one here, this is r over 2. That's this one. This one here is r over 2. And this one is r over 4. So that's our y, or our delta to y conversion. Now, let's do some combining to see how this works. So we'll keep this. The z1 here is r over 2. z2 is r over 2. And our z3 here is r over 4. Okay, now let's work on this network. I'm going to redraw it in this fashion. You can see this is this node here, and I've just stretched this out. This resistor is R over 2. This resistor is R. This resistor is R over 4. This resistor is 2R. And this resistor here is R over 2. So this part is my Y, or my star connection, that I converted from the delta that we had. So let's start combining to find the equivalent network. This we're not going to touch yet. That's R over 2. Now I can combine these two series elements to give me a single equivalent resistance. Series resistors add, so this is R plus R over 2. So this will be 3R over 2 for this one. So this is 3R over 2. R plus 1/2 R is 3/2 R. This one is R over 4 plus 2R. Or we can write this as R over 4 plus 8R over 4, or 9R over 4. So this one is 9R over 4. The sum of R over 4 and 2R is 9R over 4, or 2.5 R, or 2.25 R. So now I have a parallel combination here. So what we'll do is we still have R over 2 here, and we're going to combine this parallel combination into a single resistor. Well, there's a number of ways we can do it. The parallel combination here I'll call R parallel. 1 over R parallel is the sum of the reciprocals. Let's just do this. So I'll call this RP, the parallel combination of this. Well, 1 over RP, that is the admittance of the network, the parallel combination is the sum of the admittances. So it's the reciprocal. So it's 2 over 3R plus 4 over 9R. So putting over a common denominator of 9R, we have 3 times 3, or 6 plus 4, or this is 10 over 9R. So RP then is the reciprocal of that. which is 9R over 10. So this is 9R over 10. Now the complete combination here, RL, is just R over 2. We have a series combination here, R over 2 plus 9R over 10. We'll put it over common denominator. This is 5R plus 9R over 10, or 14R over 10, or our RL is 7R over 5. So that's the equivalent resistance looking into the network that the voltage source sees. So the current then being delivered by the voltage source is V divided by RL. Well, I'll just write it here. I, our capital I here, is just V divided by RL. Well, V, RL is 7R over 5, or this is 5V over 7R. That's the value that we had before. So once we have the total current being supplied, we can go work backwards and get all the other currents and voltages in the network as we did before. So that's another way to solve the network. Now, I said at the beginning that I'd talk a little bit about a Wheatstone Bridge. I saw in comment sections that some people seem to be confused as to what a Wheatstone Bridge is and how it relates to a bridge network. A Wheatstone Bridge is a very special bridge network. If you have a bridge network and you drive it with, say, a voltage source, let's call this R1, this is R2, this is R3, this is R4. You have a Wheatstone bridge when the ratios of the resistors in the two arms are the same. So R1 is to R2 as R3 is to R4. The reason is that you can look to see that you have two voltage dividers here. By maintaining that ratio, then the voltage at this node and this node will be identical and no current will flow in the bridge resistor. The current will be 0. That is, if the voltage divider here is the same as the voltage divider there, the voltage here and here are the same. So the voltage divider on this arm is R2 over R1 plus R2 times V. And if that equals V times the voltage divider here, which is R4 over R3 plus R4, then let's look at what the relationship is. The V's cancel. We end up with R2 times R3 plus R4, cross multiplying. And cross multiplying here, this is R4 times R1 plus R2. This is the condition for the current to be 0, because the voltages at these 2 points now will be the same. So if now we see here, well, let's multiply first through. We have R2, R3 plus R2, R4 is equal to R4, R1 plus R4, R2. For that to be equal, what needs to be the relationship here? Well, let's look at R1, R4, and R2, R3. See, this and this are the same. So for this equation to be equal, I have to make these two products the same. So we have R2, R3 equals R4, R1. Cross multiplying, then we can write R3, or divide both sides of this equation, say by R4, R2. So if I divide, let's do it this way. I'm going to divide the equation now. Remember, in order for this equation to be equal, I have to make that product equal to that product. So I'm going to divide now through by R2, R4 on both sides. We can see our R2's cancel there, our R4's cancel there. So the requirement is that the ratio of R3 to R4 has to equal R1 to R2, which is what I stated for a Wheatstone bridge. Now, the reason for this is what you normally do with a Wheatstone bridge is you can use it to determine an unknown. For example, what you normally do, instead of having a resistor in here, you might put some sort of an ammeter, a galvanometer. Now, if the bridge is balanced, where we have this condition of R1 is to R2 as R3 is to R4, then no current is going to flow in the ammeter. It's nulled out. But suppose we replace one of the resistors in an arm with an unknown called Rx. Well, if Rx is different, we have R1, R2, R4. So our R3 now becomes an Rx, our unknown. So I can write this relationship in this fashion and solve for Rx. Rx is R1 times R2 times R4. Now, if Rx is different than this value, then the bridge becomes unbalanced and the current flows. And the ammeter, the current, depending upon whether Rx is smaller than required or larger, the current will either flow one way or the other way. And if you have an ammeter, it will indicate off center. It won't be zeroed. It will be either off to the left or off to the right in the indicator. And what you normally do on something like this then is make, say, R1 a variable resistor. So you put an unknown Rx in here, then Rx is to R4 as you tune R1 so that the ammeter is reading 0. When it reads 0, then you know this relationship is holding. And from that relationship now you can determine Rx. You measure the value of R1, you know R2 and R4. Those are fixed. R2 and R4 are fixed, so that's a fixed constant. And you tune R1, so you adjust R1, you measure R1, and you determine what your unknown is. That's a Wheatstone bridge. That's how it's used for determining unknowns. And you can also do it with reactive elements where you might put capacitors, inductors in here if you want to find out the capacitive reactance or the inductive reactance of an unknown. But this is how a Wheatstone bridge works. And the Wheatstone bridge is a very special bridge network. It's a balanced bridge network. And the network that we were dealing with before was nowhere near a Wheatstone bridge. Is in our other network, what we had, our R1 was 2R, our R2 was R, this was 2R, this was R. So if we put the values in, R1 was a 2R, R2 was R, the resistor we had up here was R, and the resistor down here was 2R. So canceling out the R's, we see that this is 2 equals 1/2. So it's way out of balance, nowhere near being in balance. We have to have these ratios be equal in order for this to be a balanced Wheatstone bridge. And the way, again, that way that we use the Wheatstone bridge is we put a detector in between the two arms, and we put an unknown in one of the arm positions, and then we tune the other arm so that we end up with a null, have zero current flowing between the two arms. And what we say is we tune for a null, is that the detector in here will indicate a 0 when the bridge is balanced, and then once it's balanced we can solve for our unknown because we know R2, R4, and we measure what R1 is, and we can solve for the Rx. That is a Wheatstone bridge, and this type of a circuit arrangement was used initially for determining unknown resistors, reactances. This was an LCR bridge that you can use it to determine unknown values of inductors, capacitors, and resistors, depending upon how you select these elements for R2, R4, and R1. Now, one last thing that I can't emphasize more is that whenever you solve networks, you should check your answer. And let's look at how we might check the answer on the network that we just... One last thing before we wrap it up. Whenever you solve a network, you should always check your answers for consistency. And the way you do that is you can use Kirchhoffs Current Law to sum currents at the nodes, and Kirchhoffs voltage laws for summing voltages around loops to make sure that everything is self-consistent. Now, the network that we had is this, and here are the currents that we solved that flow in the network. The current coming out of the voltage source is 5V over 7R. The current going in the bridge resistor is flowing downward with value V over 7R. The current in the 2R resistors are 2V over 7R, and the currents in the R resistors is 3V over 7R. Now, what we'll do is let's use Kirchhoffs Current Law, which tells us that the sum of the currents into a node have to equal the sum of the currents leaving the node. So at this node, the currents coming in is 3V over 7R, and the currents leaving is 2V over 7R and V over 7R. So we can see that we have the denominators are all the same, so we can ignore those. So we have 3V equals V plus 2V. So 3V going in, 2V over 7R, and V over 7R going out. So that checks. How about here? Current coming in, and in here has to equal the current leaving. So we have V and 2V, so 3V going in, 3V going out. It checks there. How about at this node? Well, we have 5V coming in here, 2V leaving, 3V leaving. So we have a total of 5V leaving, 5V going in. So that checks. And the same thing here. We have 2V, 3V, total of 5V over 7R leaving, and that equals the current. The current has to be continuous going through the voltage source. So the current coming in equals the current leaving. So that checks. Now, how about Kirchhoffs voltage law? Kirchhoffs voltage law tells us that the sum of voltages around any loop, any closed loop, has to be equal to 0. Well, let's pick a closed loop. Let's say choose this one in this direction. Let's start here at this node. So the voltage across this resistor, if the current's coming downward, the current goes into the positive terminal of the resistor. Current goes positive there and positive there. Now, let's sum our voltages going around. Starting here, our voltage is a minus R times V over 7R. plus, we're going in the plus terminal, 2R times 2V, the current, over 7R. And then we're going into the minus terminal here. So it's minus R times 3V over 7R. Well, this better sum to 0 for Kirchhoffs voltage law. It tells us so. Well, the R's cancel. So we end up with minus V over 7 plus 4V over 7 minus 3V over 7. So we can see that that is 0. That checks. Let's pick another loop. How about if we go on the outer loop? Say go around this way. Let's start here. Current coming in, that's plus minus. And the current's going in here, plus minus. Now we're going on the outer loop. We're starting here. So we have R, the resistance times the current, which is 3V over 7R. Then plus twice the resistance of the current, 2V, 7R. Then we're going into the minus terminal of the voltage source, and we're back to where we were. So what's that equal? The R's go out, so we have 3V over 7. R's go out, plus 4V over 7, minus V, and that is 0. So that checks. And we can pick any other loop that we want. We can do, say, this loop. Let's do that loop there. So starting here, we have R times 3V over 7R. We're coming down into the plus terminal of R times 7, or V over 7R. Then we're going into the plus terminal of this resistor. So we have plus R times its current, 3V over 7R. And then we're coming back and we're going into the minus terminal of the voltage source. So what's that equal? Well, again, the R's cancel, so we have 3V over 7 plus V over 7 plus 3V over 7 minus V. What's that equal to? Well, 3, 6V, 7V over 7. So that's equal to V. So that's also equal to 0. So it's all self-consistent, but you always want to check your work to make sure that you have the current directions right and the voltage